All right, here we're looking at a worked example problem from paper 1. This actually comes from paper 13 that was administered October-November 2014. It's question number 33, and it reads, a metal wire of length 0.5 meters has a resistance of 12 ohms. We are to calculate the resistance of a wire of length 2 meters and made of the same material but with half the diameter. Immediately, you should recognize that the equation that's helpful and sort of bring some form to this is the resistivity equation. And because it's resistance that we're sort of wanting to know ultimately, I'm going to write the equation in terms of R. So R equals resistivity times length divided by the area. Without this equation in mind, there's really no way to move forward. You know, like if you don't know that equation, then you're kind of just guessing. Okay, so at least we can kind of say, okay, well, here's the equation that sort of relates to the information I'm given. And so here we can think about we were given an original length, L. We were given a resistance, R. Being told that it is made of the same material is saying that the resistivity is the same, right? Resistivity is that sort of property of the metal that says how well will it conduct, okay? So it's measured in ohm meters. All right, and then the area and the length are all, are sort of the two things, along with the type of metal it is, that sort of determines the final resistance of that metal resistor. What kind of metal is it? What's its resistivity? How long of a path do the electrons have to flow through? And how wide of a sort of corridor do they have to flow through? So the wider it is, then the less resistant. The longer it is, and the more resistant. And the combination of how sort of wide and long we sort of coil up a little piece of wire inside of a little tiny, resistor, that determines whether it's a 12 ohm resistor or a 48 ohm or a 96 ohm or 192 ohm, right? But it's made of the same metal. Okay, so just different length, different area, right? They doubled its length, but they half its diameter. And we have to consider how does that change the area, all right? So the strategy that I was referencing earlier in terms of how to solve this is look at proportions. We want to really set this up as a proportion, comparing sort of the resistance of this to the resistance of the new one. And I prefer to kind of set up proportions to make the thing that I'm sort of solving for, what is the resistance of this second wire? Okay, so I'll call it R2. I want to put it in the numerator, compared to like R1 over here. So I'm going to call this guy here R1, which means this is L1. The resistivity is the same, so you can call it 1, 2, whatever. Like that's not going to change, right? So it's like what are we manipulating? So you just sort of write down, okay, I want a ratio of these resistances. And so we just use the equation and say, okay, well, this is everything with R2. So it's like so it's equal to the resistivity of 2, which is the same as 1, right? So just for kind of completion's sake, I'll write all of the subscripts. All right, now this would be the length of the second one. And what do they tell us? Or we could say, comparing it to this one, how many times bigger is this? If this is L.5, then this is what? Four L, right? It's 4 times bigger than that. Do you agree? So I'm really going to say, well, R2 here is the same resistivity, rho, but it's 4 times as long, okay? Divided by, now I got to think about the area here, okay? If I half the diameter, what did I do to the area? The area, the cross-sectional area of a wire is a circle, okay? This is a circular cross-section, and the area of the circle is pi r squared. If you half the diameter, don't you half the radius also? So if you are 1/2ing the radius, then you are 1/2 squaring the area. In other words, the area is proportional to the radius squared. So if you change the radius, by a factor of a half, then you change the area by a factor of a half squared, or 1/2 squared is 1/4, right? So by halving the diameter, what you're really doing is you're getting a cross-sectional area that is 1/4 as big. It doesn't just go like, oh, we half this, and so this is half as much. The 1/4 as much. And so the area of the second one is going to be, let's just use this, 0.25. The area of the first one. Okay, so I'm just sort of calling all of these things like it doesn't matter what the area is. See how they don't ever tell us that. They don't ever say, you know, has an area of however many meters squared. So it's like it kind of forces us into this proportion to just like compare. Well, we'll just call this length L then, and this is 4L, and we'll call whatever this area is A, and the new area is 0.25A. And so everything down here, like, so this is everything with R2, right? It's rho, it's L, it's A. R1 was just, everything was a unit, right? Everything was just one. We said if this has an area of 1, and compared to this one, this is 0.25, whatever that 1 is. So that's sort of the power of the proportion, is that we're just comparing two sort of values here. And this is actually enough to solve it. It looks like a monster. I know it's like, oh, I don't know. Complex fractions, the name sounds bad. Fractions are already tough enough. I think there's complex fractions. All right, A over B over C over D is AD over DC, right? Because we're dividing a fraction, which means we multiply by the reciprocal. So it should make sense that like, oh, if we're dividing by this, we're multiplying by that, so AD over BC. So I don't know how or when, but I always tell students this will save your life one day. Okay? AD over CD is AD over BC. A over B over C over D, AD over BC. Okay? Very useful to kind of keep that in mind. Look what we got over here, A over B over C over D. Okay? So now I'm going to rewrite this. R2 over, remember what R1 is, has a value, 12, equals. Now, this is my A, this is my B, this is my C, and this is my D, right? I've got a fraction and a fraction. So AD, so the numerator over here is going to be this term, rho 4L times A, right? Over BC, so I have rho L and 0.25A. Okay, so far so good, everybody? Everybody follow this so far, or at least taking the notes down, you can reference it later. It's not quite clear yet. We're solving for R2, right? What is the resistance of this second wire? The rho's cancel, the L's cancel, the A's cancel. That's why we use the proportion, because we just say, hey, it doesn't matter what these things are, like those are just going to cancel out. All that matters is like the coefficients, like how did we change them compared to the other one? Because we know the first one is 12. So if the second one is like 4 times as long, but a quarter is, you know, the area, then we're going to have this perfectly solvable algebraic sentence here. It's going to look like this. I'm going to write it right over here. And you probably already beat me to it. You probably already know. Oh, I know how to do this now. So this is going to be 4 over 0.25. Okay. Multiply this out by 12. 4 times 12. So R2 is 12 times 4 divided by 0.25. So that's 48 divided by 0.25. That's 48 times 4. That must be this number. All right, 48 times 4. 2, 3, 1, 9. So it looks like D is the right answer. 192 ohms. I hope. Unless I made some error that other students typically make when they solve this, that's why that answer is there. It's like there's always an answer that's like captured that do something that's a typical mistake, and hopefully that I didn't make a typical mistake this time. That is the right answer. How would we check? How would we give ourselves the feedback that we want right now to say, yeah, what we did right there is good stuff. Well, you take that to the bank and do that every time. What would you want to do here? Correct. Check the marks. So question 33. In this paper here, I'm going to go back one. This is winter 14, paper 1333. So I got winter 14, paper 13, right? Paper 13, question number 33, and we're looking for D. Nice, D, so that's good stuff. All right, so I really encourage you all to go on to whatever sort of website resources that you have access to, and just kind of do the same thing. Question, try your hand at it, try to set it up, use your notes, and then give yourself immediate feedback by just taking a look at the mark scheme and saying, okay, yeah, I got it, I'll do the same thing again. Or if it's incorrect, try to see if you can't figure it out, so like where you went wrong, and kind of prove to yourself in your mind, oh, this is how you go about this kind of calculus, because I know the right answer is this. Okay, and then please bring any questions that's like, oh, I found a really good one. Question 34 was really tricky. I couldn't even figure it out. And I know the answer is, but I can't, figure out why. Those are really good ones to talk about because some of these questions I'm telling you are really, really tricky ones. That if we can figure those out, we can figure out anything. Okay, so the more, not just practice problems. The point isn't just to like do a bunch of practice problems. The point is to use it as a problem study. We're using this problem to study all the physics that's sort of contained in there. So it really doesn't matter what kind of question they ask. We understand the physics so well, we can feel anything, right? That's sort of the goal. So keep on going, Monday, paper one day, and we'll maybe try to set up some lab work.